Swayam Prabha. Digital India. Educated India.
Welcome to 13th lecture of video course on Tribology. Present topic is lubrication mechanism. In previous lecture, we understood boundary lubrication mechanisms. We discussed two modes of boundary lubrication mechanisms. To compare all lubrication mechanisms, one convenient method is straight curve. Straight curve is basically a curve between coefficient of friction and a bearing number. Bearing number can be defined as sliding velocity, what we are talking about the relative sliding velocity, lubricant viscosity per unit load. Unit load means the applied load divided by projected area. When we plot coefficient of friction with a bearing number, what we get are different domains, different regimes of lubrication. Here we are able to see a broken line, or there is no continuity from 0 to some point. That is indicated when relative velocity is 0, then this system will not act as a Tribos system. That means we cannot plot these results with a 0 velocity. That is why there is a discontinuity. Coefficient of friction does not mean for the 0 velocity. Other than what we talk about the static coefficient of friction, what we are talking about the kinetic coefficient of friction. And coefficient of friction is unitless. It is a force divided by force. Now, this curve, red color curve, has a 3 domains indicated with a dashed ellipse. First is boundary lubrication. Second is a partial contact lubrication. Third one is a hydrodynamic lubrication. We can extend this also. We can say initially it will be dry contact, or when we are not intending any lubrication mechanism. Lubrication is happening its own or is happening because of the environment. We are not giving any lubricant to the surface. When we do intentionally some lubrication on the surfaces, then it will be called a boundary lubrication mechanism. Boundary lubrication mechanism basically is a solid lubrication. A solid form of the lubricant remains intact with the surface. If it is a 1 molecular thick liquid layer, then it will act as a solid, and it can be called as a solid lubricant, it can be called as a boundary lubrication. Other domain here, it is shown a hydrodynamic lubrication, where the relative velocity is essential and lubricant viscosity plays major role. If I compare hydrodynamic lubrication with the boundary lubrication, what we can see in boundary lubrication, lubricant chemistry and the chemistry of the surface of metals which are interacting plays an important role. The chemistry important, while in the case of hydrodynamic lubrication is a viscosity or resistance to flow is more important. We know very well that nothing will be absolute. There is a possibility of mixture of these two. Few surface asperities are covered with the boundary lubrication, and few asperities are not covered, or if it is covered, they are not in contact. They remain separated due to the lubricant film. That is why there is called a hydrodynamic lubrication. There are other domains also, what we call the minimum domain of the lubrication here. When the coefficient of friction is minimum, often it is known as elastohydrodynamic lubrication. So, depends on bearing number, we can divide lubricant regime in 4 categories, in 4 broad categories, what we call as a boundary lubrication. And if you want to develop a new category, which is a dry lubrication, and when there is no intended lubrication, that is also possible. Second one is a mixed lubrication or partial contact lubrication. Mixed lubrication mechanism is more common, or is very commonly used compared to the partial contact lubrication, and finally comes to the hydrodynamic lubrication, where here intermediate will be elastro-hydrodynamic lubrication, where basically mechanism will be hydrodynamic lubrication mechanism, but in along with that we will be considering elastic deformation of surface and viscosity thickening effect that will increase the load carrying capacity. In fact, what we say, almost every element need to have elastro-hydrodynamic lubrication mechanism if we are really worrying about the cost, if you are worrying about optimum performance. Optimum performance happens at that point. Now, if I think from a stability point of view, stability means if a system is disturbed, it should come back to its original position or regain its position without going unbound vibration or going towards a failure. So, if I go ahead with that kind of thinking, stability thinking, I can say this is a boundary, this is a line. If I see the right hand side of this line, this is a stable domain, stable regime. What is why we are saying the stability, or why we are emphasizing this domain is stable? Let us take an example. We want to operate at this point. Lubrication mechanism is getting operated at this point where there is a certain velocity, lubricant viscosity and unit load. Now, because of the heat, temperature will increase, and because of the increase in the temperature, separation between molecule will increase. That is going to cause a lesser viscosity. That means, if we started point here, it will decrease. Because of lesser viscosity, bearing number will decrease and then coefficient of friction will decrease. As the coefficient of friction is decreasing, naturally heat generation will decrease or heat production will decrease. That is why the heat generation will be decreasing, that will lower the temperature. If the temperature is lowered, it is going to gain back the normal position. Or what we say that even if we operate somewhere here, stability will be remaining there. It is not going to unbound, it is going on a better condition, it is going to be self-helping, it is a system helps itself in that case. So, it is a stable domain. If I see the other side, left hand side of this line, if I do not consider right hand side, I consider only the left hand side. Now, if in this case heat generation is high, temperature is high, and because of the that viscosity is decreasing. Decrease in the viscosity will reduce the bearing number. If the bearing number is decreased, this is going to further increase the coefficient of friction. Increase in the coefficient of friction will increase heat generation. Increase in heat generation will increase temperature, that will reduce viscosity. So, this is a compounded effect. Once it is disturbed, it will ultimately reach to this condition where the coefficient of friction will be enormous, maybe say 0.5, 0.6, and a system which was not supposed to design, or we were not designing the system with coefficient of friction more than 0.1, in that case coefficient of friction reaches to 0.5, 0.6, naturally system will collapse, system will fail. That is the reason why we call this domain is in a stable domain, in a stable regime. That is why whenever we want to operate any system, we should operate with the right side of this line, not the left hand side of this line. But if there are restrictions, that system cannot be operated at right hand side, because of the some lubricant restriction or supply of the lubricant, or we cannot go ahead with the liquid lubricant at all. In that situation, we need to design a system with a narrow band, assuming, and we need to keep a control on the temperature. That means, we need to provide artificial cooling, so the temperature should never go beyond certain limit. Now, that is that was a Strybeck curve. It can conveniently describe what are the regimes and how one regime will be differentiated with other regime. Now, come to the mixed lubrication case. Why we are saying the mixed lubrication? Because in this contact pair, when they say the machine element 1 and machine element 2, when they are at the interface or we are making interface, we are able to see there are few asperities which are directly in contact. There is no lubricant, or there is no boundary lubricant at all. Few asperities where the boundary lubricants are acting, at few asperities only the liquid lubricant is there. That means, there is a possibility of dry friction without any boundary additives. there is a there are few contact with the boundary additives, few contacts with liquid lubricant, and few contact where the elastic deformation has happened. You can see this surface is elastically deformed. It is showing a much more smoother surface compared to the valleys and peaks which are shown on the other surface. Similarly, there is elastic deformation over here. So, there is elastic deformation, there is a boundary additives, there are liquid interfaces also, and there is a dry contact. This is why we are calling it as a mixed lubrication. There is a part dry lubrication, there is a boundary lubrication, there is a liquid or fluid film lubrication, or if there is a relative velocity, then it will be called as a hydrodynamic lubrication, and there is a possibility of elastohydrodynamic lubrication. So, you can say there is a dry contact, boundary lubrication, elastohydrodynamic lubrication, and fluid film lubrication. If I mix all together, that makes mixed lubrication, and that was shown in the previous slide. Mixed lubrication, that is a longer one lubrication mechanism, where almost all the mechanisms are interacting with each other and giving overall results. We try to analyze whatever system you pick up, then if you analyze that lubrication mechanism, by and large it will be mixed lubrication mechanism. Now, there is a possibility only 1% is a dry lubrication, 5% boundary lubrication, 10% elastohydrodynamic lubrication, and remaining fluid film lubrication. Depends which mechanism is dominating. If a fluid film lubrication is dominating with 90 to 95% asperities are separated because of the fluid film lubrication, then it will be called as a hydrodynamic lubrication or fluid film lubrication. I am using the word fluid film lubrication compared to hydrodynamic lubrication because there is a possibility of separating two surfaces by inducing outside pressure or supplying pressure from outside. That will be called as a hydrostatic lubrication. It will not be called a hydrodynamic lubrication. That is why to differentiate that, we are talking about the fluid film lubrication. Fluid is there, from where and what is the source we are not talking. There is a possibility of a squeeze film action also. So, hydrostatic, squeeze film, hydrodynamic lubrication, all they try to separate the surface completely. There is no asperitic contact in those situations. Now, as I mentioned, there is a possibility of change in weightage, but we say that weight can be given W1, W2, W3, W4, and summation of weight should be equal to 1. That means, if there is a 1%, that means W1 is a 0.01, W2 is a 0.05, that is a 5%, W3 is a 10%, 0.10, that remaining 85%, that will be W4 that can come from this equation. Now, it depends on the which mechanism and how we are lubricating the surfaces, this overall equilibrium can be established, and that is going to decide what will be the friction and wear characteristics of that interface. If W1 has a higher value, if W1 is a higher value, naturally friction will be higher, wear will be higher. If W4 is a very on higher side, then naturally the lubrication is effective, wear will be turn out to be 0 or negligible. Friction then they will depend on the viscosity of the lubricant. If we are operating the viscosity a higher thick using the thick lubricant and operating at the higher speed, the friction will be higher side. That was also indicated from the Strybeck curve. If friction is sliding velocity is higher, and that too in fluid film lubrication mechanism or in hydrodynamic lubrication mechanism, in that coefficient of friction will be on a higher side. So, depends which characteristics we want. We want higher lubrication or high coefficient of friction, but lesser wear rate, naturally we will keep a high relative velocity and thick viscous fluid. So, the two surfaces are completely separated, but it can develop a high coefficient of friction, it can give a high coefficient of friction. To find out the coefficient of friction in mixed lubrication mechanism, we can go back to our previous relations which we derived using junction theory, or we say junction growth theory, where the mu was expressed in terms of shear strength of interface and shear strength of bulk material or soft material having a shear strength in a bulk form. So, coefficient of friction was derived from using that relation. If I think from a mixed lubrication point of view, I can say this tau I, the shear strength of interface, will be function of interface which is made because of the dry lubrication, direct metal to metal contact. So, I am expressing tau m I as a metal interface, then tau B L I, that B is the boundary, L is lubrication, I is interface. That means, due to in a boundary lubrication interface, what will be the tau? Then comes the tau E H L I, E is elastro, H is hydro, and I is interface, and L in this between is a lubrication. So, elastro hydrodynamic lubrication interface, and last one comes, that is a FFLI, that is a fluid film lubrication interface. Now, there is a possibility of generation of fluid film lubrication, and that will give some friction because of the shearing of that lubricant. And if there is elastic deformation, the deformation will consume some energy, and that is can be directly related to viscosity increase. But we can say depends on the relation, depends on the elastic deformation, viscosity of the lubricant will increase, and that is going to increase coefficient of friction, particularly in this situation. Then comes the boundary lubrication, that can be estimated. However, if we are not 100% sure, then we can play, or we say that we can use some sort of software to do iteration to find out W1, W2, W3, W4 by collecting the experimental data on that. And this is some note comes where here we say that tau metal, shear strength of metal will be greater than shear strength of boundary lubricants. Shear strength of boundary lubricant will be greater than shear strength of liquid lubricant. We have not talked about the gas lubricant, but if there is a gas, or maybe say that air, or maybe gas, maybe nitrogen or hydrogen also, then in that case shear strength of that interface will be lower. Or another case, we can say the gas bearing, any solid surface separated by the gas as a lubricant will have a lowest coefficient of friction. Interface separated, obviously that two surfaces separated by liquid lubricant will be having intermediate or coefficient of friction greater than gas, but there is a possibility of a lesser coefficient of friction compared to boundary lubricant compared to metal contact lubricants. Now, if I assume fluid film lubrication is a Newtonian fluid lubrication, or the fluid which is being utilized is a Newtonian lubricant, in that case the tau FL Li can be represented or can be given in this form, is a eta and velocity gradient. Eta will be in a Pascal second or millipascal second, u will be meter per second, and then this y is in meters. So, if I take some magnitude analysis or some approximation, what we can say, assume the oil which we have used has 10 centistroke as viscosity. 10 centistroke is something like a 10 millipascal second. 10 millipascal is equal to 10⁻²⁰ Pascal seconds. And velocity, if I can roughly estimate, maybe say around 10 meters per second, that is a relatively high velocity, and separation between the surfaces or which is happening is maybe around 10⁻³ or say 1 mm. If I go ahead with this calculation, what we are going to get is something like 100 Pascal. 100 Pascal is a very low shear strength compared to the boundary lubricant, which may have a strength when they are getting attached to the surface in megapascal also. So, 100 Pascal versus in megapascal, even 1 megapascal makes a difference of 10,000. But we can say that this shear strength will be roughly 0.1% or much lesser than that also. It will be lesser than that. Now, if I think about the viscosity thickening effect because of the elastic effect, then it will be 20 times, maybe say 20 multiplied 100 2 kilopascal. Again 2 kilopascal will be much lower shear strength compared to solid material shear strength, which may reach around 200 megapascal. A boundary additives, then it may be around 100 or 120 megapascal. That is again a very huge difference in shear strengths. So, to be on a easier side, I can assume these two terms are negligible when we think about coefficient of friction. and when we are talking of the mixed lubrication. Of course, if we talk only about the fluid film lubrication, in that case we need to account this, even the whatever the lowest coefficient of friction we need to estimate through that, or with the EHL we need to estimate coefficient of friction, but that will be not relative, that will be in absolute sense. When we are relating it, we know this coefficient of friction, this fraction, even though the 5%, 10% may contribute a significant factor in deciding overall coefficient of friction compared to FFLI and compared to EHLI. Keeping that in mind, we will consider these factors whenever there is a mixed lubrication mechanism dominated with metal and boundary lubricants. Of course, if there is 95%, 97% FFLI, then we should include all the factors. Then there is a possibility 50% or 25% coefficient of friction is given by the fluid film lubrication also. This example or this experimental readings were shown in one of the previous lecture. I am just repeating it so that we can utilize our relation whatever we have concluded from our previous slide, and give some mathematical treatment, get a result from that angle. In this case, what we expressed earlier, that when pure mineral oil is used at the interface, coefficient of friction was 0.360. We are talking about very low relative velocity, we are talking about very high load. In all those situations, boundary bearing number will be almost negligible. So, we can say the fluid film lubrication even in the presence of pure mineral oil was a negligible. Now, we added 2% oleic acid. In that case, what will happen? Coefficient of friction turned out to be 0.249 or 0.25 roughly. Increasing on oleic acid is decreasing the coefficient of friction, but not to a substantial level, and subsequent increase in oleic acid is not going to give us much results. So, as in this case fluid film lubrication is not dominating factor, or elastohydrolytic lubrication is not dominating factor, I can use thinking about this one also, and more or less asperities will be in contact, or asperity covered with boundary additives will be in contact. So, we have used this relation alpha tau mi and 1 minus alpha tau BLI. That means, we are assuming W3 is equal to 0, W4 is equal to 0, W1 is equal to alpha, and remaining W2 which can be find out we can figure out from equation W1 plus W2 plus W3 plus W4 equal to 1, that will give us a result W2 is equal to 1 minus alpha. Now, we can utilize this relation along with this relation to find out what will be the interface shear strength for the metals and liquid interface, metal interface, and what was shear strength of boundary lubricant interface. That means, if I use a coefficient of friction 0.36 in this relation, tau I can be figured out if I know the tau y. For most of the metal, tau y is known to us. That means, if I know the coefficient of friction, if I know the tau y, I can figure out easily tau I. Let us take an example. In this case, where we say that alpha is equal to 1, liquid lubricant was not acting at all, and boundary additives was not mixed in that. So, alpha equal to 1, that means 1 minus alpha will be equal to 0. This shear is 0. Whatever the tau y, it comes because of the metal interface. Or we can say directly, instead of writing tau I can write here the tau mi divided by square root of tau y square minus tau mi square. If you use this relation, so the 0.36 is equal to 1, is alpha is equal to 1 over here, tau mi divided by 2, the same 2 is getting repeated over here, square root 200 square minus tau mi square. Now, I can simplify this equation, I can figure out what is the meaning of what is the value of tau mi, which is happening because of the metal interface, and that turned out to be 116.86 megapascal. That means, if the bulk shear strength was 200 megapascal, this turned out to be 116.7 megapascal. That is a reasonably high value in absence of boundary additives, but liquid lubricant acted very nicely. They have given some interface, sliding interface or able to reduce the shear strength of interface, and that happens always. Wherever there is adhesive bonding, use a lubricant, then there will be slippery action happening there, and cold weld junction will not happen if there is a slight relative velocity. Of course, if there is an excess wear load, even in that case, in presence of a liquid, there is a possibility of cold weld. But if there is some lubricant available, load applied is high, even in that case interface shear strength will be lower than bulk metal shear strength, which is by and large happening whenever we do experiments in the lab. We found interface shear strength is lower than bulk shear strength. Now, we will take another example. We know that coefficient of friction is not decreasing further. Here 0.198, that means all the sites are being occupied by boundary additives. That is why the coefficient of friction is not varying after that. When all the sites have been occupied by boundary additives, there is no further site available which was empty. In that case, I can assume that alpha is 0, whole the surface being occupied by boundary additives. If I make alpha is equal to 0, that means that tau I will turn out to be tau B L I. I can substitute over here tau B L I, tau B L I. I know the coefficient of friction, that is turning out to be 0.198. And I can simplify, I can find out interface shear strength, that is turning out to be 73.64 megapascal. Mind it is in megapascal, it is not in kilopascal, it is not in pascal. When we talk about the fluid film lubrication, we were talking about the only pascal, not even reaching to the kilopascal. When we are talking about the EHL and viscosity thickening effect, then there was a possibility of some kilopascal, say 1-2 kilopascal. But in absence of those lubrication mechanism, when you are talking about the boundary additives, just monolayer or very thin lubricant layer on a surface, maybe say in some nanometers, that coefficient of friction is reasonably high, but whole the surface covered with boundary additives. Now, I can find out any value intermediate, that means I can find out the mixed lubrication, what is happening in this case. Third case was 2% oleic acid, that was a mixed lubrication in that case, and we are able to find out the results. In this case, the 0.24 is 49 coefficient of friction, 200 megapascal as the shear strength of metal, and finally, when we are using this relation or we are able to find out alpha. We can go ahead with the reverse side. We can find out what is the tau I, substitute tau I, we know tau m I, we know tau B L I. I can find out what will be alpha. I will just repeat it. It said in third case, when the coefficient of friction is 0.249, substitute 0.249. Tau I is known to us, tau I is not known to us. So, express tau I in terms of whatever the mu directly results, or in terms of tau I and mu, or you can directly interpret the result what is the tau I, substitute tau I over here. We already know what is the tau m I, which came out to be 116.86. We know tau B L I, which came out to be 73.64. Substitute this value, I can figure out what will be the value of alpha. That means, either if coefficient of friction is something like a 2469, I can figure out what is metal to metal contact. It says that 36% of asperities are directly in metal to metal contact. There is no boundary additive lubricant on that, or maybe it is a depleted, boundary additives have reduced, or more boundary additives can be added. This kind of methodology, this kind of mathematical treatment allow us to do the optimization, how much lubricant additive should be mixed at 3%, 4%, 5%. It can be iterated accordingly. Of course, this is a very simplified expression. It does not hold always, but it gives a reasonably good idea about the boundary additives or percentage effect on surfaces. Now, we will come to the wear mechanism, what we are talking about the wear in mixed lubrication. It is interesting. First and fundamental rule says that wear will never occur because of its own. Only one mechanism will not finally lead to the failure. It is always a mixture of lubricant wear mechanism which will cause final wear. First thing is that in dry lubrication there is a possibility of a strong aberration, a strong adhesion, but when we talk about the lubrication mechanism or we talk about wear in lubricated conditions, then there is a possibility of some sort of adhesion where the asperities are still in a contact, some sort of corrosion, maybe lubricant is corroding the surface or some process fluid getting mixed with lubricant causing the failure. And finally comes the fatigue. Fatigue will be always there. Okay. Whenever the lubricated wear, adhesion can be avoided, abrasion can be reduced, but fatigue will be dominating factor in that situation. So, what we are writing in this case as a volume per unit length per unit sliding distance is getting contributed by V A, that is volume wear due to the volume per unit sliding distance wear due to the adhesion. Here the volume wear because of the corrosion, volume wear because of the fatigue, and there is a possibility of interaction. Adhesion and fatigue, they are interacting together. Corrosion and fatigue, it has happened that whenever there is a corrosive environment, fatigue will be enormous, or what we say the fatigue effect will be enormous. And finally comes aberration, whatever the particles are getting detached or coming from the environment, they are causing the wear of the surface, losing the wear material, that means can be added on this. Now, question comes, how many experiments really will be required to get all these parameters? Huge number of experiments are required to conclude that way. That is why it is not a very common approach. Of course, this is an ideal approach, but it is not a common approach, reason being that there is a complexity of wear processes. Predicting the result with 100% accuracy from wear experiment is still not possible, except the nano level. Now, when things are not 100% sure, that we will not be able to get a good results from that. That is the reason why we are constrained, or what we say, whatever we do, we are not going to get a fruitful results from this kind of approach. That is why we are not going out of this approach. What we say, we are not going at the superposition imposition of individual component of wear. We need to think from some other angle. And previous slide we have shown that friction calculation and how we can go ahead with this kind of calculation. That is why this is another way to treat say that get a comparative results. But we are talking about the wear lubricated or wear under lubrication, wherever there is a lubricant available and still a wear is happening 100%, that will cause a lesser wear compared to unlubricated, because aberration, more and more rolling action will occur, and in that situation aberration will wear will decrease. Similarly, there will not be many junction due to adhesion, so wear will go down. That is why they say that wear lubricated by wear unlubricated will be equal to some fraction, that is a beta, and this beta will be lesser than 0, lesser than 1, but greater than 0. And few experimentalists they have done an extensive experiments, and then they could relate beta with alpha. So, basically wear is happening because of the friction junctions. If there is no friction junction at all, there will not be any wear. If there is adhesion, that is why the wear happen, adhesive wear. If scratching happens, or the plowing is happening, that is happening because of the friction mechanism, that is why the abrasive wear comes into picture. Similarly, fatigue will happen because of the some sort of confinement and some sort of coefficient of friction, that is causing some adhesion, loosening some particles from that. So, everywhere wear is related to friction. We are not talking the direct relation, magnitude relation, there is a possibility of change, but when a lubricated condition, it can be related. Again, this is a hypothetical concept, whatever the experiment were done, based on that this judgment came. It will not be 100% true for each and every case. If this is a situation, I can utilize this expression to find out alpha. Once alpha is known, we can find out what will be the wear volume reduction. We can say whether the beta is equal to 0.01, 0.1, 0.2, 0.3, that can be judged relatively, not absolutely, relatively in terms of alpha. That is a good approach. Instead of going with extensive experiments based on superimposition of individual wear mechanism, this requires much lesser number of experiment and then give some sort of conclusion which is reliable for most of the materials. There is another possibility that if we do extensive experiment in the lubrication mechanism and in the absence of lubrication mechanism, alpha can be figured out using this relation also. If we do the, we know this alpha will be statistical, and then we can find out the mean value from that. If I know mu under lubricated condition, mu in absence of lubricant, and mu under normal condition which we are operating. We are not we are talking about the mixed lubrication, where there is some sort of lubricant, the liquid lubricant will be there to separate the asperities, some sort of metal to metal contact will be there. That is why we are going ahead with the first absolute sense. Only liquid lubricant completely separated. What is the coefficient of friction? What is the coefficient of friction with the mu coefficient of friction on the metal to metal interface when there is no lubricant at all? And what is the coefficient of friction under actual condition which is required to perform experiment? In that case, if we know the mu, we can find out alpha. If I know the alpha, I can find out the beta. That will give us results how much friction, how much wear can be reduced by using the lubricants or lubricant additives, or we can find out the effectiveness of the lubricant. Let us take one example. We say, suppose we did an experiment with and found the coefficient of friction under metal to metal interface with a 0.6. Take an example of steel. Mild steel can give the coefficient of friction equal to 0.6. Now, you have given a cupous flow. You have completely separated two surfaces, and the shearing is happening. If there is a relative velocity that is causing some sort of shearing of lubricant, and that is causing a coefficient of friction equal to 0.05. That means, I know the mu m, I know the L, I can find out if there is a mu different mu in the different regime, I can find out alpha, and that will give the beta. So, let us this theoretical study, but we say that let us take an example of the mu is equal to 0.5. That means, whatever the real condition, mixed lubrication condition we did, some sort of liquid lubricant and some boundary additives, coefficient of friction turn out to be 0.5. Again, as a hypothetical. In that situation, if we substitute value and figure out alpha is turning out to be 81.8%, or say compared to metal to metal lubrication, it is reducing by around 18%, 18.1%. So, coefficient alpha is 0.8181 or maybe say 0.82, but beta is lesser. That means, where having a lubricant has a more effect on the beta compared to alpha. Same thing, if I go to the different kind of boundary additives and coefficient of friction is turning out to be 0.4 instead of 0.6, then this alpha value is decreasing, because metal to metal interface is decreasing. In that case, it can now turn out to be 0.64, while beta is 0.51. Again, the beta is lesser than alpha. We keep going doing the same thing, coefficient of friction is reduced to 0.1, and we say the coefficient of friction 0.1, alpha is also 0.1, is only 10% metal to metal contact, while in this case it is turning out to be only 0.03. That means, instead of 10% what we are talking metal to metal interface, but where is happening at only 3%. That is what we are trying to conclude is lubricant has a more role, more effect on the wear compared to the friction. That is why we say that we are not agreeing with the definition of lubricant. If you see the definition of lubricant in a common English dictionary, we say that substance which reduces the friction, but here we can talk that the substance which reduces the wear as a predominantly and friction also. So, it reduces the friction as well as wear. More emphasis is given on the wear. You can see the comparison here, the 3% and 10%. Reduction is by 97%, while in this case reduction is by 90%. Another domain as I mentioned, the mixed lubrication and hydrodynamic lubrication comes elasto-hydrodynamic lubrication. So, a few lines are written over here. We say that in rolling contact elements, whatever the rolling action is happening, when we studied earlier that the fatigue is the main value wear phenomena. In that case, what will happen? The fluid film will not be very high, liquid lubricant film will not be dominating, and whatever theoretical analysis, simple theoretical analysis we do, what we find in that case is something like we get film thickness much lesser magnitude, but in actual case when we do experiments we found the film thickness is a greater side. Theoretically we are not able to get the results if we go ahead simple with hydrodynamic lubrication mechanism. However, we will be treating that in the next module when we exclusively come up with equation, Reynolds equation and elastic equation, try to solve the equations. If we do that, whatever the if we use only the hydrodynamic action, then film thickness will be much lesser, but in reality when we do experiment we find the film thickness is greater than that. And this is what we are talking about, the this domain somewhere here, elastodynamic lubrication. It is not reaching to hydrodynamic lubrication, bearing number is not that high as required for hydrodynamic lubrication. One guess, rough guess says that because of the high pressure, liquid molecules will come closer and closer. If molecules are coming closer and closer, they will give more and more resistance to the fluid flow. A more resistant to fluid flow, that means viscosity is increasing. Effective viscosity is higher in these cases. That means, if viscosity is higher, film thickness will be higher. That is a one good guess, and the person who has given, he developed also relation and what we call as a Barrows relation. Now, Barrows relation says that viscosity will increase with the pressure, and this is exponential relation. There are a number of other relations also, but not all the researchers are coming to the same conclusion, and we are here to explore these lubricant regimes. We are not going to the research front, is more like learning and then maybe subsequently implementing according to that. What it says that there is alpha, what we call as a piezo-viscous coefficient, and that is generally expressed in terms of per unit Pascal. For most of the liquid, this will range between 1 to 2. For mineral oil is a 1, or synthetic oil it may be slightly higher, or for some thick oil it may be higher. So, alpha, higher value of alpha means higher viscosity and a high pressure. To just elaborate that, I have given this table over here. We say that let us assume alpha is equal to 1, alpha is equal to 1 and increase the pressure. Pressure is only 10⁵ Pascal. That means, this is 1 10⁻⁸ into 10⁵, that means it will be 10⁻⁻3. When 10⁻⁻3, the viscosity will be almost the same as eta 0, that is ambient pressure. That is what we kind the multiplication factor is a 1.001, which is a negligible, is comparable to 1. Now, we increase the pressure by 10 times. Instead of atmospheric pressure, we increase pressure to 10 times, that is the almost 1 megapascal. When 1 megapascal, we are able to see there is an increase in viscosity by 1%. 1% increase in viscosity, what we say that this is the multiplication factor, is exponential alpha p is factor that will instead of 1, it will turn out to be 1.01 when the pressure is 10 bar. Now, pressure is increased to the 100 bars. This factor turn out to be 1.1, that means 10% increase in the viscosity. Instead of 100, it goes to 1000, okay, that means 100 megapascal. In case of 100 megapascal, this factor has increased substantially, it is coming out to be up 2.7. That means, there is an increase in the viscosity by 170%, and that is a thickening effect. Further, if it goes to the gigapascal, 1 gigapascal, you can see the viscosity increase in 22 times. And that is the reason given for the rolling element, maybe rolling element bearing or the gears, wherever we required increase in a viscosity, because if the load is very high and we do not want the lubricant turn out to be or squeezed out of the interface, we want viscosity increase at that point, and it happens because of the lubricant property itself. AR increasing the viscosity tremendously from 1 to reaching to 22 times. 22 times increase in viscosity. Of course, it is when the contact pressure is 1 gigapascal, which is not very uncommon. Contact pressure can reach to even 3 gigapascal, 4 gigapascal because of very high loading. And it is interesting to note that most of the load is shared by liquid in this situation. So, what we say that this is important, this kind of fact is important whenever there is a heavily loaded concentrated contacts. And the one problem comes. You say that even the high pressure, it will take some time to rearrange the molecule. It will not be spontaneous, it will not happen in 1 nanosecond. It may take a few milliseconds to the second to reach to that equilibrium. It will take some time. That is why the effect may not be that dominating at what we are showing. There will effect, if this is happening, talk about the example of rolling element bearing. It may take hardly 1 second or lesser than 1 second in a concentrated contact, and after that the ball goes out or rolling element goes out from the contact. So, we will not be able to reach to this effect. Effect may be a 50%, 40%, 70% depending on relative velocity. That means, whenever we go for very high load, bearing should not be operated at the very high sliding speed. They should be operated at the low sliding speed whenever there is a very high load. Under those situations only this viscosity increase will be substantial. If we are operating very high load and very high speed, then this will not be dominating factor. Alpha only a fraction of this factor will be a factor, and we should use some other relation which can account velocity effect in that. Now, some interesting thing about elastohydrodynamic lubrication or some sort of a mechanism which can be proposed. What we say that under mechanical loads, every surface deforms. That is by and large true. Deformation may be a nano level, but deformation will be surely there. And we say that if there is a deformation, there is a possibility of dragging that lubricant into that interface. And if there is a dragging of lubricant at the interface, pressure will increase. This is the common example for the rubber seals. The rubber itself is a very soft, even 10 megapascal can deform the rubber substantial level. Similarly, this kind of mechanism occurs the gear teeth where the viscosity thickening effect occurs. Now, to illustrate that, let us take one rubber material, rubber sheet, and there is a shaft, maybe say assume the steel shaft which will not deform, as Young's modulus is far higher compared to the rubber material. So, if there is a load on the shaft, deformation of the rubber will happen, something like this. If there is a deformation and if we pour the lubricant, because of the rotation, lubricant will be brought into this this kind of interface, which can retain the lubricant for some time compared to the straight surface. It is making a shape in such a manner, so it can act as a reservoir for the lubricant. That is helping us. The deformation and then further subsequent to that is a viscosity increase, that both will act together and then can give us a very favorable environment for the tribo interface, where the friction will not go very high value because there is a change and there is a change in the film thickness itself. I am just trying to compare when the shaft comes in a contact with the rubber, there will not be any film thickness of liquid, but because of the rotation as well as the deformation of rubber, you are able to see some sort of interface here or some sort of film thickness over here. That is caused because of the elastic deformation, and that was in previous slide when we mentioned about effective film thickness will be larger side what we can estimate from hydrodynamic lubrication. If we are estimating a hydrodynamic lubrication some x unit, and because of the EHL there is a possibility of 5x film thickness, increase in a film thickness. That is happening because of the elastic deformation as well as because of viscosity. Some conclusion marks from the elastohydrodynamic lubrication, which is the film pressure even the 10 megapascal is sufficient to deform the surfaces to submicron to micron level, and this is causing the alteration in the gap between tribo surfaces, tribo pairs. The gap is happening because of that. To analyze, to come up with some results on elastohydrodynamic lubrication, we can combine elastic deformation of tribo surfaces, increase in viscosity as well as hydrodynamic lubrication. So, we are treating in three ways. First is that we require elastic deformation we require increase in viscosity and we require hydrodynamic lubrication. But this says clearly that the increase in viscosity from previous table was shown to us is that if pressure is not very high, then there is a possibility of increase in viscosity, but not to a greater level. When we talk about something like a 100 bar or 10 megapascal, we found increase in viscosity is only 10%, it is not very high percentage. And again, if there is a relative velocity effect, velocity is higher, and means the rolling contact is not happening for the longer duration, then thus viscosity effect will not be dominating also. But we are hypothetically thinking about 10%, it may not turn out to be 10%, maybe 2%, 3% depending on the relative velocity. So, that may not happen substantially, that is why we differentiate between elastohydrodynamic lubrication, what we call is soft EHL and hard EHL. Soft EHL means elastic deformation can be considered, but not a viscosity effect or not viscosity thickening effect. And other mechanism what I talk about a hard EHL, where the viscosity as well as the deformation need to be considered. Both the surfaces are hard, it requires substantial pressure to deform the surface. If surface pressure is very high, then viscosity effect also will be dominating. Of course, to some extent it will be decreased because of the velocity effect. Right. Now, we did some case study in our lab, what we picked up two bearings. One is made of brass material, other is made of acrylic. Acrylic is a softer surface, that can be also figured out from this one. So, compressive strength in acrylic is roughly 50 megapascal, but the brass is a 300 megapascal compressive strength. And their density, acrylic has a very low density, so that is advantages. There are some factors which we say the melting point of the acrylic is lesser than 130, that means we should not apply too high ambient temperature or should not induce a too high ambient temperature. Another reason to avoid high temperature application is low thermal conductivity of acrylic material. Now, what we did experiments by making a brass bearing and acrylic bearing on one test setup, what we can name as a journal bearing test setup. That looks like something like this. The journal bearing test setup, there is a bath where filled with a lubricant, that means whole bearing will be submerged, and there is a bearing attached to this load cell at the bottom. This is a brass bearing. There is some load arrangement, the load lever, we can apply a load from one end and it will be pushed with a leverage mechanism on the other end. We can regulate the speed of pressure sensor. What is we have applied a pressure sensor to measure the pressure of what is the pressure at the interface. So, that we can find out whether there will be elastic deformation or not. That is why the pressure sensor comes, and this bearing rotates after certain duration that can be fixed as per our own algorithm. At every 9 degree it will rotate, or at every 9 degree it will change its position after certain duration. Maybe say time t is equal to 0, it is as a 0 degree. Maybe after time t is equal to t1, it will rotate by 9 degree and again it will stop. So, that we can cover whole circumference to find out the pressure profile. And this was a one brass bearing here, and similarly bearing was made for the made of the acrylic material, which is softer material having compressive strength only 50 megapascal, while this having a compressive strength of is a 300 megapascal. Now, we compare the results. When we are comparing the results of coefficient of friction and P maximum, by P maximum which occurred in acrylic bearing and P maximum which occurred in a brass bearing, both are in a kilopascals, and maybe of course in few places only it has reached to the megapascal. But acrylic material is a softer material, it will be deformed at the low contact pressure itself. Few experiments were done in the 500 rpm, 1000 rpm and 1500 rpm. Again the four kind of the loads, the 300 Newton, 450 Newton, 600 Newton and 750 Newton. Coefficient of friction is not a very dominating factor in this case, because it is happening at the decimal level. As the second decimal is not be very important. What is more important for us to find out the pressure, maximum pressure. What we find the maximum pressure in the first load situation, first load and speed situation is around 572 kilopascal, while brass case this maximum pressure is 696 megapascal. So, the interesting thing is that material properties are playing important role in finding out what will be the maximum pressure. This is good to learn from mechanical engineering point of view. Reason being, many times in mechanical engineering we design component and subsequently we select the material based on the maximum pressure, without thinking the maximum pressure itself will be decided by the load component or the material which is getting deformed, or we generally avoid the deformation and then calculate maximum pressure, while in a reverse case or in a reality or a practical situation, deformation will change the maximum pressure value. This is happening over here, same load situation, same speed condition, but maximum pressure in this case is happening around 696 kilopascal, while it is happening here maybe say around 20% lesser than 572 pascal. Same situation as speed is kept the same, but load is increased. We can see from 572 it has reached to the 1331 at 750 Newton meter, while brass case it is reaching to 1620 kilopascal, or we say the 1.62 megapascal, while in this case 1.3 megapascal. So, again a 20-25% difference in the maximum pressure happening because of pressure. Now, if we increase the speed from the 500 to 1000, pressure is increasing, which is clear. In hydrodynamic bearing cases, the increase in speed will increase the maximum pressure value, its load carrying capacity will increase, and the pressure profile will be in the much lesser extent, not much lesser extent. So, in this situation what we are getting, and slowly it is increasing and then subsequently decreasing in elastic deformation case. Now, this is interesting to note. Here the surface is also getting deformed. As the surface is getting deformed, it will flatten, and if it is a flattening, the most of the surface, not most of the surface, a reasonable surface will be having maximum pressure. It will not be only one point pressure, but having a surface pressure. While in this case, we are able to see that pressure has increased and has increased to 1.8 megapascal. Now, if we further increase the speed from 1000 to 1500, what we are able to get something like maximum pressure here as a 1.3 megapascal, while in case of the brass is turning out to be 2.6 megapascal, 1.3 megapascal versus 2.6 megapascal. That is the interesting thing. We have brass, maximum pressure is going on a higher side compared to the acrylic material, because acrylic material is deforming and it is adjusting it. That is the reason why we say that elastic deformation should be considered whenever we are analyzing any practical situations. If the pressure is sufficient to deform bearing or deform bearing asperities, then factory lubrication mechanism is elastro-hydrodynamic lubrication mechanism, is not only the hydrodynamic lubrication mechanism. And this is what I am trying to conclude present lecture with the two graphs. We are showing here in the, this is a more like of a rigid case, and this is for say elastically deforming surface, even though materials are same. Here the material thickness is roughly 3 mm, here material thickness is reaching slightly lesser is around 200 micron size. We can see clearly over here that there is a flattening, and we will elaborate this in our lecture on elastro-hydrodynamic lubrication mechanism, where we deal with a number of mathematical equations. Thank you for your attention. We will continue next lecture with hydrodynamic lubrication mechanism. Thank you.